kinetic energy and the work-energy theorem. Here we have a scenario where an object moves along this path from moment 1 to moment 2. We see the velocity of the object indicated at moment 1 and at moment 2. We see the displacement vector, delta r, pointing from the object's location at moment 1 to its location at moment 2. And we see the net force vector that the object is subject to all along this path, shown here, broken into components as well. And lastly, we have the angle between that constant net force vector and that displacement vector. So we'll use this scenario to illustrate the derivation of kinetic energy. We can compute the net work done on the object, assume it has mass m, by a constant net force between moments 1 and 2, using network formula number 2. We will derive an equation that will relate the initial speed and the final speed, and this equation will be called the work-energy theorem. So starting with formula 2 for computing net work. We're going to take the x component of the net force multiplied by the x component of the displacement and add to that the y component of the net force multiplied by the y component of the displacement. That is the product of the parallel parts of the net force vector and the displacement vector. Here we introduce Newton's second law, some physics we already know. The acceleration in the x direction is given by the net force in the x direction divided by mass, likewise for the y direction. So we can rearrange those expressions to write the net force x component as mass times the x component of the acceleration, and the y component of the net force as mass times the y component of acceleration. And I want to substitute these max and may expressions in here for net force x and net force y. So subbing those in gets us to this point. And now I want to introduce some more physics we already know. A constant acceleration kinematics equation we're familiar with. That is, the change in the square of the x component of velocity equals 2 times the x component of the acceleration times the delta x, and likewise for the vertical direction. So with these, given that our expression has ax delta x here, I'm going to rearrange this to get the ax delta x by itself. Essentially, I'm just going to divide both sides by 2 to get ax delta x equals 1/2 times the change in vx squared, and likewise here for the vertical side. And I'm going to substitute this expression in for ax delta x up here in our net work equation. So that's going to go in there, and then this is going to go in here. So making those substitutions, we get mass times 1/2 delta Vx squared plus mass times 1/2 delta Vy squared. Of course, a delta anything is the final value of the thing minus the initial value of the thing. So V2x squared minus V1x squared, that's this. Over here, likewise on the vertical side. And I'm going to gather the final x and y v squared values, this v2x squared and v2y squared. I'm going to get those two terms together, moving here. And the minus v1x squared and minus v1y squared, I'm going to bring those two terms together over here. So we've got collections of final values and collections of initial values. And we see that we've got actually, by Pythagorean theorem, v final x squared plus v final y squared. Well, that's just our final speed squared. And likewise, v initial x squared plus v initial y squared, that's just our v initial squared. So the net work simplifies down to this, the difference between the final value of 1/2 mv squared and the initial value of 1/2 mv squared. And this invites us to define something we're going to call kinetic energy. The kinetic energy of an object of mass m with speed v is defined as 1/2 mv squared. Note that kinetic energy is always non-negative by definition, since mass is positive and our speed squared is also going to be positive or 0. The SI unit for energy, this is the first energy we've discussed, is the joule. Capital J is the abbreviation for joule. So a kilogram for mass times a meter per second squared is equivalent to 1 joule. A joule is the same thing as a kilogram times a meter per second squared in our SI system. So what we found here is that the net work done on an object subject to some net force between two moments is equal to the difference in the final kinetic energy and the initial kinetic energy of the object. Final 1 half mv squared minus initial 1 half mv squared. So that's the delta kinetic energy, capital K for kinetic energy. So the net work on an object is equal to the change in kinetic energy, the delta K on that object. And this formula is known as the work-energy theorem. Checking our units here, we've got work on the left, which has SI units Newton meters, and kinetic energy on the right, which has SI units of joules. And it turns out here that those units are identical to each other. A Newton meter of work is the same thing as a joule of energy. What this expression is telling us, what this equation is telling us, this principle, is that work represents a transfer of energy. And since the work-energy theorem spells out the word EWalk, this EWalk is here to tell us that work done by a force transfers kinetic energy. Positive work is going to cause a positive delta K, meaning positive work adds kinetic energy. Negative work means a negative delta K, meaning negative work removes kinetic energy.